Hello, I'm Omar Al-Naggar from the Department of Mechanical Materials and Aerospace Engineering at the University of Liverpool. I'm presenting my research as part of the University of Liverpool Doctoral Network in AI for Future Digital Health. My research is closely related to human motion analysis, specifically wearable sensing for non-invasive human pose recognition during sleep. I'll start off by presenting the unmet needs that my research is trying to fulfill. Then I will illustrate how that is being accomplished and the results which have been arrived at in the course of this work. Finally, I will leave you with a concluding summary, future work directions, and a list of key references. First, the research motivation. My research stems from musculoskeletal disorders, which are often caused by injuries or could develop due to genetic factors. Today, there are slightly over 200 different musculoskeletal conditions, many of which significantly limit one's mobility and dexterity, making them a leading contributor to disability worldwide. Unfortunately, due to the reduced ability to take part in professional and social roles, musculoskeletal conditions bring about other comorbidities, usually depression, obesity, and diabetes. We are now talking about a health condition that affects between one fifth to one third of people in different countries across the globe. For example, in the UK, it accounts for over 25% of all surgeries taking place in NHS hospitals. In England alone, musculoskeletal conditions make up 30% of GP consultations. I myself was one of them. um, Out of the 200 musculoskeletal disorders, my research particularly focuses on plantar fasciopathy, commonly known as gastrocnemius contraction. Its main symptom is pain in the soft tissues of the heel and bottom of the foot. The pain is severe in the morning, lessens with walking, but worsens again towards the end of the day. Clinicians suggest a number of factors that could lead to this condition, primarily the tightness of the calf muscle, also obesity and standing jobs, all of which exhaust the lower limb muscle tendon units. Now let's have a look at the current practices available to this subgroup of patients. Frankly speaking, the current practices are not very useful as you might expect. Traditionally, clinicians start with conservative treatment, which comes in the form of an ankle rest pad or a night splint. This treatment aims to avoid placing any pressure on the ankle joint. If these symptoms continue to persist, invasive surgical treatment may be considered, where the level of intervention varies from one patient to another. But in principle, it aims to manually relieve the tightness of the calf muscle tendon unit. Until today, we are lacking tools not only for the early diagnosis of this condition, but also for quantifying the success of treatment, as it is entirely based on patient feedback. In this project, we decided to take a step back and have a more holistic overview of the situation. Statistics show that on average, a person sleeps for 8 hours, about one third of their lifetime. So we asked ourselves, isn't it worth looking at how we sleep? This question will help us verify the untested clinical hypothesis that there is a correlation between sleeping poses and the development of musculoskeletal disorders in the long term. From there on, a collaboration is formed with Dr. Lyndon Mason, an orthopedic consultant at Aintree University Hospital in Liverpool. Now, let me tell you more about what we are actually looking for in our sleep. Most reported most reported work on sleeping pose classification normally considers only four standard sleeping poses: supine, prone, and left and right lateral positions. Such a coarse classification is actually of limited use for the intended clinical purpose. Upon discussions with Dr. Mazen, we have expanded the study to include the 12 sleeping poses shown on the left. We have also identified a list of deliverables to accomplish throughout the project. It all starts with a novel sleep monitoring technology in which a minimally invasive network of inertial sensors distributed over the human body is used to track in body postures. We then need to stream these data to a central database for storage and processing. This will help us understand the relationship, if any, between how we sleep and the likelihood of developing a musculoskeletal health condition. It will also allow us to monitor the success of treatment as it takes place. Next, let me illustrate to you how is this being accomplished on a lower level. Now I will be presenting the methods and main findings of our research. First of all, the project is broken down into 3 phases. In the first phase, we perform human motion analysis in virtual environments, which emulate realistic conditions. Phase 2, which we are currently at, it involves the development of an embedded system for the wearable devices. Finally, validating the proposed approach will take place in phase 3 during the clinical trials. Here is a system block diagram of the proposed approach in phase 1. The primary tasks belonging to each subsystem are discussed. Since we started off by emulating human motion analysis in a virtual environment, we used Blender, an open source computer graphics software. Then we modeled the human skeleton within the software and incorporated the necessary joint constraints to ensure plausible body poses during the animation. We then performed a virtual limb calibration procedure to identify the anatomical axes of rotation of critical joints with respect to a reference frame. Finally, we produced an animation clip in which the human character model replicates the closed set of sleeping poses. But the animation clip provides scarce data that is insufficient for training a machine learning algorithm. We therefore introduced new augmented limb orientation data to our training dataset. With the resultant enhanced training dataset, we then implemented a multi-class classifier to map the limb orientations to the set of sleeping poses. Here, you can see the produced animation clip. The alien-like character model, I like to call him Omarika, is shown on the right, and the output of our skeleton tracking algorithm is displayed on the left. In here, the character model sequentially replicates all the sleeping poses, separated by an intermediate calibration T-pose. The next step was to parameterize the sleeping poses. This is based on tracking certain limb orientations and linking them to the respective sleeping poses. It has been agreed that we will only consider the 4 extremity limbs, both wrist and ankle joints, unless more observability of the body pose is deemed necessary. The tracking process normally prerequisites a limb calibration procedure, which is proposed in our paper to be presented later in this conference. Shown in the left figure is an example of how we are able to track the local wrist joint frame with respect to a reference global frame. The frame transformations are presented using the axis angle kinematic representation. Then the pose-dependent transformations are augmented using our novel jittering-based technique to produce enhanced datasets for classifier training. Now, I would like to talk about the classifier implementation. Motivated by their high performance across different applications, support vector machines have been chosen for the classification stage. Since SVMs are originally suited for binary classification problems, therefore, an error correcting output codes model, shortly known as ECOC model, is employed. As observed from the block diagram of the ECOC model illustrated on this slide, it first breaks down the 12 class classification problem into a set of binary classification subproblems, each handled by a binary SVM learner. Then the vector of combined classifier outputs is compared against the reference code word associated with each of the 12 classes using the Hamming distance measure. Finally, the predicted class is assumed to be of the minimum Hamming distance. The ECOC model performance was evaluated on several augmented datasets produced using different hyperparameter settings for the proposed data augmentation technique. The mean and standard deviation of the pose classification accuracy were regarded as primal as primal performance metrics. It has been it can be seen that high generalization performance is maintained, um, as high as 100% classification accuracy with minimal deviation levels. Um, if you would like to know more about the methods of our research, I welcome you to attend my technical paper presentation later in this conference on the 17th of December during the medical and legal applications session, in which I will cover the list of points on this slide in more detail. Here in this section, you will find a concluding summary of the presented research, directions for future work, and a list of key references for further reading if you would like to. Thank you for your attention. I'm more than happy to have your questions now.